Chapter 9, Section 6. In the final section of Chapter 9, we'll take a look at how we can maximize a function with two variables that is bound by a set limit. These types of limits are common in real-world applications, and having a tool to maximize functions with such limits can be helpful. For instance, a company that wants to manufacture a certain product would be limited in the amount of raw materials it could use because of its budget. When we maximize a function that has this type of limit, it is said that we are finding the function's constrained optimization. Let's take a closer look. So let's say that a quantity Q of a good that we want to produce depends on the quantities X and Y of two raw materials used. So we want to make something using two different materials represented by X and Y. Our level of production is represented by the function Q equals x to the 0.3 times y to the 0.7. Let's also say that material X costs $10 and material Y costs $10 and our budget is $50,000. We can represent this using our budget function 10x plus 10y equals 50,000. That sets up the maximum amount of money that we can spend constrained by our budget. So let's start simple. If we spend $10,000 on material X, how much can we spend on material Y, and what would our production be? And for part B, what if we spend $30,000 on material X? How much can we spend on material Y, and what would our production be? Okay, so again, our production function is x to the 0.3, y to the 0.7. Our budget function is 10x plus 10y equals 50,000. If we spend $10,000 on X, then we have $40,000 left to spend on Y. Knowing this, we can find the production level. So we want to start by finding the value for each variable. So if we're going to spend $10,000 on X, and in our equation that's represented by $10 times the number of units we produce X, that means we'll be producing 1,000 units of the raw material X. That leaves us with $40,000 to purchase Y. Well, it's $10 for each part of the raw material, which means we can buy 4,000 units of our raw material Y. To find the production level, we need to take these two values and plug it into our Q function. So here, as you can see, we're plugging in 1,000 for X, 4,000 for Y. We plug those numbers into our Q function, and we get that we can make approximately 2,639 total products. So that means that 2,639 units can be made if we spend $10,000 on X and $40,000 on Y. For part B, we now want to spend $30,000 on material X, and that means we'll have $20,000 left to spend on material Y. So again, let's start by finding our production level for each one. If we spend $30,000 on material X, that means we're going to purchase 3,000 units of it. If we spend $20,000 on Y, again, we're just dividing by this 10Y. That means we're going to buy 2,000 units of Y. And our production level, we now calculate by plugging in 3,000 for X and 2,000 for Y. We plug that into our production function, and we get approximately 2,258 units that can be made if we spend $30,000 on material X and $20,000 on material Y. So in part A, we were able to produce 2,639 units when we spent $10,000 on material X and $40,000 on material Y. However, when we changed that amount and we spent $30,000 on X and $20,000 on Y, we were able to make only 2,258 units, which is 381 units less. So from a business perspective, the first approach would result in a higher profit. Well, we obviously want to figure out the most number of units we can make. So what if we wanted to know the right price combination of material X and Y that would optimize our production level while taking into account our budget? So we call that our constraint, and we represent this by the function g of xy equals c, our constraint. So this is where we get something called Lagrange multipliers. So suppose a P0 is a point satisfying the constraint, so something that keeps us within our budget or whatever our constraint is, then our function will have a local maximum at this point subject to the constraint if the y values are greater than all other y values for points near p naught satisfying this constraint. And our function will have a local minimum subject to the constraint if the y values of the function there are less than all other y values of points p satisfying this constraint. So our local and global minimum have similar definitions that we looked at in the last chapter. How do we use these Lagrange multipliers? What do they mean? How do they function? Alright, let's check it out. Okay, so the method of Lagrange multipliers, they're used to optimize the function within a constraint by solving the following equations. So we want to take the partial derivative with respect to f and set that equal to what we call lambda, that's this symbol here, this is the Lagrange multiplier, times the partial derivative with respect to x of our constraint. We also want to satisfy that the partial derivative with respect to y of our function should equal lambda times the partial derivative with respect to y of our constraint, and we need to satisfy our general constraint. So that means we're going to have three unknowns, x, y, and lambda, and so we want to solve for each of these. If f has a constrained global max or minimum, then it's going to take place at the solution of these three equations. So let's see how we do this with the problem that we've been working on. Okay, so we want to find the value that maximizes production using values from the previous example, but with the limits that x has to be positive and y has to be positive, because it doesn't make sense to have negative raw materials. So our production function was q equals x to the 0.3 times y to the 0.7, and our budget constraint was 10x plus 10y equals 50,000. Over on the right, you can see the equations we want to satisfy. So that means we need to get some partial derivatives so that we can set up our equations. The partial derivative with respect to f of x, here, that means y is a constant. So the partial derivative says the 0.3 comes down out front and subtract 1 from the power. So the 0.3 comes down. If you subtract 1 from 0.3, you get negative 0.7. Y to the 0.7 was a constant. It was multiplied, so it just sticks around. The partial derivative with respect to y means that now y is our variable, so x is just a constant. So the 0.7 comes down out front, x to the 0.3. And now 0.7 minus 1 is negative 0.3. We also need our partials of our constraint. So the partial derivative of g, which is our constraint, with respect to x is going to be 10. The derivative of 10x is 10. And the derivative of 10y is 0, because that's a constant. The partial derivative with respect to y is now going to be 10, because the derivative of 10y is 10. The derivative of 10x is 0. So now that we have all our partials, we want to set up our three equations. So the first equation should be the partial derivative of f with respect to x equals lambda times g partial with respect to x. So our partial with respect to f looked like this, equals lambda, and then our partial derivative of the constraint with respect to x was 10. Our second equation was the partial derivative with respect to y equals lambda, partial derivative of g with respect to y. So we take our partial f function and set it equal to lambda times partial derivative with respect to y of the constraint. So again, lambda is 10. So then we also need to satisfy our general constraint, which is 10x plus 10y equals 50,000. Now that we have our three equations set up, we want to be able to solve this simultaneously. How you solve is going to depend on what you end up with for your equations. So our three equations that we just set up are up top, and we want to notice here that the first two equations both equal lambda times 10. If two equations equal the same thing, they must equal each other. So our first equation equals lambda times 10, our second equation equals lambda times 10, so they have to be equal to each other. That's going to help us to solve. So we set these two equations equal, and we're going to use algebra to solve. So what we're going to do is bring all the y's over to the left. So that means we have 0.07 divided by y to the negative 0.3 on the left. On the right, we're going to have 0.7 x to the 0.3 divided by 0.3 x to the negative 0.7. Now notice that on the left-hand side, the y values, we can bring this term up by making the power positive. So this is equivalent to y to the 0.7 times y to the 0.3. On the right-hand side, again, we can bring the bottom term of x up by making the power positive. So we have 0.7 divided by 0.3 equals x to the 0.3 times x to the 0.7. Remember, if you multiply two things that have the same base, you add their powers. So 0.7 times 0.3 gives us y to the 1 on the left. On the right, 0.3 plus 0.7 gives us x to the 1 on the right. And 0.7 divided by 0.3 is 2.33, 3 repeating. So we've rounded it to 2 decimal places. So now we have y equals 2.33x. Well, this is very handy. We use the first two equations to get something in terms of x and y, and now we can use our third equation, our constraint equation, to actually solve. So here, our constraint says 10x plus 10y equals 50,000. We substitute in y equals 2.33x, and that gives us what? 10x plus 10 times 2.33x equals 50,000. That's going to simplify, combining like terms, to 33.3x equals 50,000, or x equals approximately 1502 units, 1,502 units. Once you have x, we know that y equals 2.33 times x, so that tells us that y will be 3,498 units. So the optimum value will occur when x is 1,502 and y is 3,498. If we plug these values into our original production function, we can find the actual value that maximizes this production. We found the raw material values, but let's find the actual level of production. So our original equation was q equals x to the 0.3 times y to the 0.7. We plug in our x and y values, and we get that the level of production will be 2,715. So the maximum value of f is 2,715, and that occurs when x equals 1,502 and y equals 3,498. So we used this Greek letter lambda in the previous example for Lagrange multipliers, but we didn't actually give it a value. So we can actually solve for lambda using one of our partial derivatives with the equation, along with the fact that we're using x equals 1,502 and y equals 3,498. So again, one of our original equations is that we were looking at the partial derivative of f with respect to x, and that equals lambda times the partial derivative with respect to g at our production level. So the equation for our partial derivative with respect to x of f was 0.3 x to the negative 0.07 y to the 0.07 equals lambda times 10. Plugging in our values here that we got for the optimum solution, we can solve for lambda, and we get lambda is 0.054. This value represents the extra production we achieve by increasing our budget by $1. So lambda in general is represented by the change in the optimum value of f divided by the change in g, our constraint. So the value of lambda is again going to be part of the optimal problem that relates the value of the function in terms of how much we're changing our constraint. So the value of lambda, is going to be looked at as we increase our constraint and we see how that affects this optimum value. Let's look at another example, because not all examples have the fortunate property that they'll equal the same lambda times some constant. So we'll see how to solve if that's not the case. So if x and y are the amount of raw materials used for the quantity q of a product, and now q will be x times y, we're going to assume that x costs $20 per unit and y costs $10 per unit, and our production budget is $10,000. So that means 20 times x plus 10 times y is 10,000. Again, x and y will be positive or 0 because it doesn't make sense to have negative raw materials. So we want to find how many units of x and y should be purchased in order to maximize production, how many units are produced at that point, and we want to find the value of lambda. Okay, so again, we want to set up our Lagrange equations. So we're going to need to find partial derivatives of f, partial derivatives of y, and set up our budget constraint. So our production function was xy, so let's do our partials. So the partial derivative of f with respect to x, remember x is our variable now, and y is a constant. If you have a constant times x, the derivative is just that constant. So f sub x is just y. Similarly, if we take the partial derivative with respect to y, that means y is our variable and x is our constant. Constant times y, the derivative is just that constant. So now, when we do the partials of g, so here, the partial derivative of our constraint, g, with respect to x, the derivative of 20x is just 20. The derivative of 10y is 0, because that's just a constant. Partial derivative with respect to y of g, 20x, the derivative is 0, because that's a constant. The derivative of 10y is just 10. So now we have all the pieces we need to set up our general equation. So again, our general equations look like this. So we have f sub x equals lambda times g sub x. So that gives us y equals lambda times 20. Then we also have f sub y equals lambda times g sub y. So that gives me x times lambda times 10. And our budget constraint was 20x plus 10y equals 10,000. So again here, we don't have the same value on the right with our lambda. So we need to take a different approach in solving this problem. So our equations are just written again at the top. So since we have something for y and something for x, what we're going to want to do is plug them into our constraint equation. Because if we do that, then our constraint equation will have everything in terms of lambda. And it'll get rid of the x and y variables, and we can solve for lambda first. So here, we start with 20x plus 10y equals 10,000. That's our general equation. So now for x, we're going to plug in lambda times 10. So we have 20 times lambda times 10, plus, now instead of 10y, we have 10 times what y equals, which is lambda times 20, equals 10,000. Simplifying, we get 200 lambda plus 200 lambda equals 10,000. So that gives us 400 lambda equals 10,000. So lambda will equal 25. So now that we know what lambda equals, we can go back to the original equation and plug in that value of 25 for lambda to get values for x and y. So y equals lambda times 20. So y equals 25 times 20. So y equals 500. X equals lambda times 10. So that's going to give us 25 times 10. So x equals 250. So again, we just took our value of lambda and plugged it back into the original two equations. The endpoints of the constraint are going to be 0, 500 and 0, 1000. And since both those are going to be 0, the maximum value is going to occur at our optimized point of 250 for x, 500 for y. Plugging that into the production function, which was x times y, we get 250 times 500, so the optimal production is 125,000 units. Production is maximized to 125,000 units when 250 units of x are purchased and 500 units of y are purchased. The unit lambda equals 25. This tells us that production will go up by 25 units if the budget is increased by $1. So again, by changing that constraint and seeing how much the function changed, that relates our lambda to our x and y values. If you want to see more problems worked out with Lagrange multipliers, please check out the handout at the beginning folder in Chapter 9.